Hello, everyone, and thank you for joining me today. Here with me today, my name is Anuj Soni, and really excited to chat with you. If you are joining on Wednesday, May 4th at 2 p.m. Eastern, we are live. So we will be taking questions along the way. I already see some people chiming in here with hellos. So hello to everyone who is here with us. Just some quick background about myself. I am a certified instructor here at SANS, where I teach and co-author the FOR710 reverse engineering malware course. I'm also the author of this new FOR710 advanced reverse engineering malware course. And in addition to those two roles, I'm also a threat researcher and reverse engineer at BlackBerry. So again, very, very excited to share with you information about this brand new course. It's been a long time coming. I know it's a bit cliche to probably describe this course of mine as my baby, but it really does feel that way, because when I started developing this course, I actually only had one kid and now I have three. So perhaps that's a testament to how long it's taken for me to push this out there, and I have no qualms about blaming my children for the delay in getting this course out. But thank you again for joining. The purpose of this live stream here today and of this video is to introduce to you this new course, as well as answer any of your questions. So I will be keeping an eye as we go through the next 60 or so minutes here on the comments, and I'll be doing my best to go ahead and make sure I don't miss any of the questions, but our moderators here at SANS will also be helping me out with that. So I'm going to go ahead and just dive right in here. I do want to say, before I get into the actual preview of the material, just in case you got to hop out of this live stream, because I know life is busy at some point today, I want to call out just a couple quick details about the course. One, the very first public live run of this course is just about a week and a half away, and we do have a few seats remaining. So if you're interested and available, it begins on Monday, May 16th. It is a 5-day course, so I'll talk a little bit more about the layout here in a moment. And the on-demand version, because I know people are interested in that kind of medium of course delivery as well. On-demand is going to be released a bit later in July, but you can get information about these dates and more detail about the course if you go to sans.org/FOR710. And that link is here, and we'll be posting that in the comments as well. All right, so just in case you have to hop out at some point, I wanted to get that information out there quickly. But let's go ahead and start talking about the actual course. Now, one of the big questions I get about this course, given that in the title it has the word advanced, is what does that really mean, right? Because using the term advanced, particularly I think in our field, is a little bit charged, perhaps a little bit controversial. And so I want to be very straightforward about what we mean by that. And the simple answer is that advanced in the context of this course simply means that we're picking up where we left off with the FOR710 class. So if you've taken that class, that means you know everything you need to in order to take this course. Now, if you haven't taken 610 yet, okay, while it'd be ideal for you to go ahead and try that one out first, you just need to make sure that you have some of the fundamentals of reverse engineering under your belt. What does that mean? Well, that means you should be able already to look at the static properties of a file. That means looking at simple things like strings, looking at the import address table, understanding basics of the PE header and what comprises that portable executable file format. You should be able to perform behavioral analysis. That means likely using tools like Redshot and Process Monitor, looking at running processes with Process Hacker, taking a look at what's happening on the network with Wireshark, right? That's something you should feel comfortable doing in a virtual environment. In addition, you need to have some prior exposure to code. Okay, and by that I mean x86 and x64. This course, like 610, focuses on Windows executables. And so the expectation is that coming into this course, you've done some debugging in a program like x64 debug. You've used a tool like IDA or Ghidra in order to perform some static code analysis. You have an understanding of key instructions, like what a call is, how arguments are commonly passed to functions. You understand how to take a look at return values. You understand how to look at the control flow of a program, how to identify loops and how that loop is iterating. And so those are just some examples of things that you really should have under your belt before coming to FOR710. Okay, so again, when I say and when I use the word advanced, totally understand that if you've been doing this for 2 decades, that means something to you versus someone who has only maybe had a year under their belt. That means something different to you, right? The goal is and the purpose is to kind of be a follow-on to 610, which means you have some of the basic skills I just laid out already kind of in the rearview mirror, and you have some, hopefully, some not only some theoretical exposure to it, but also some practical on-the-job exposure. Just taking a look here to see if we have any comments so far. So one of the first questions here is there a certification for FOR710 as there was for FOR610? So that certainly is an understandable question, right? I understand certifications are important for people, important for management who might be requesting permission to actually take this course. That is going to be in the works, but typically at SANS, when a new course is pushed out, the certification comes a bit after that, right? So the course has to have some runtime first, and then a certification will be produced at a later time. I don't have a definitive timeline for that, but I'm going to throw a ballpark out here of maybe about a year-ish. But again, please don't hold me to that. That's a decision that's kind of made outside of myself, and just stay in touch with SANS to determine when that will happen. But I certainly hope, and the expectation is that a certification will be created at some point in the not so distant future, hopefully. Okay, so Israel, thanks for that question. So what I'm going to do now, and the layout for what I'd like to present to you here today, is I'm essentially going to go through the individual sections that comprise the course. There are 4 sections that you see on the left-hand side. And then I'm going to just very briefly touch on all of the modules in each of these sections. So my goal here is to give you a taste of the technical aspects of this course. Now, if we only have an hour together, I can't actually get into the details of all the slides I'm going to show you, but I wanted to show you some real slides from the course so you have some sort of an understanding of what technical depth we'll be touching, and maybe that will help you determine if this course is in fact right for you. Now, you also see labs mentioned here, and if you've seen this course description on the SANS website, you'll see references to these same labs names. I'm not going to talk in detail about these labs, but I'm leaving them up here just to give you a taste about the actual application here. Now, at a high level, the way the course is laid out is that it is 5 days of lectures and labs, okay? And this might seem a little confusing because you see 4 sections on the left-hand side, but those 4 sections, those 4 books, which is what you would physically get, are actually spread out over the 5 days. After those 5 days of lecture and lab, we actually have a CTF, and I'll talk a little bit more about this towards the end of our hour together. But that CTF is what we're referring to as an extended CTF, which means that you actually have 2 weeks after the course ends, right, after the 5th day, to actually complete the CTF. And I'll talk more about what I feel are the pros and cons of that, but I want to make clear that this is a 5-day course with a 6th day that's essentially extended. That's on your own after the lab and lecture, the live session, if you're taking the hybrid or live online or in-person version, after that actually ends. But I'll touch more on the CTF here as we proceed through the content. So section 1 is called code deobfuscation and execution. Okay? Section 1 is called code deobfuscation and execution. And the general idea here, as you can see in the first module on the right-hand side, is to get into the idea that most malware these days, as you may have been exposed to prior to this, is multi-step in its execution, okay? Typically, there's one initial, perhaps, executable that's launched that may pull down additional executables from the internet, or it may unravel during execution some shellcode, or an additional Windows executable in memory. And so what we want to start doing as we begin this course is laying down the foundation to understand exactly how that works, so we can identify the code and the algorithms that are actually being implemented in the code to actually perform that work. Okay, so one other point I want to make about this course is the ultimate goal here is to equip analysts and students to write deep dive malware analyst reports, right? So you've probably seen some of these reports that the number of different vendors and organizations put out there on a routine basis, reports that go very much in depth into the malware functionality and its capabilities. And so in order to get to that level of detail, you have to understand a large portion of the code that is embedded within a program, not just one thing it might do, but all possible capabilities that are embedded in the actual program. And so that's why we're taking a deep dive into deobfuscation. The goal is to understand how something is actually being deobfuscated, the algorithm being used to do so, being able to label those functions accordingly within Ghidra in the case of this course, and to kind of proceed through most of the functions, right? Because generally when you're doing a deep dive into malware, you usually have not only hours, but typically days or weeks to do this sort of work. So you have the time to kind of think over the sample and to dig deeper. And the first module here tackles the notion of deobfuscation. These are some of the objectives, right? The general idea, as I just mentioned, is to identify the code where it's actually performing deobfuscation, to be able to actually communicate that, right? Because that's ultimately what would you'd have to put into a deep dive report. Understand the functions and Windows APIs typically associated with allocating memory in preparation for that deobfuscation, to dive deeper into this notion that most malware is multi-component and identifying those various components that might be both on disk and in memory. And this last bullet might be a little odd to you, to develop comfort with non-binary formats, right? What am I referring to? That might pique your interest a little bit. And the reason I mentioned this particular objective in this module is because we look at a particular case study that involves the use of steganography in malware. So there are many different ways that code can be obfuscated, that this next stage execution, whether it's shellcode or a Windows executable in memory, that content can be obfuscated. One interesting application of that is steganography. And so that's actually one that we tackle in this course. This is one that's certainly on the more complex side of the spectrum, and that's why I chose it. It is an advanced course after all. And so we're taking a look at some of these more interesting applications of obfuscation, and we're going to talk about steganography specifically. During this module, we're going to actually get into code and examples, and you'll have an opportunity to look at this in a lab environment as well, where you're going to dig into the actual code responsible for destegging, essentially, some content in order to reveal another Windows executable in memory. So again, not going to go through this actual code. I'm just giving you some exposure to the technical content. And this is code that essentially takes advantage of a particular steg technique called LSB, where data is embedded in the least significant bit of bytes within an otherwise benign file format, like graphics file formats, or maybe a WAV audio file, right? That's a hint to what this sample in particular is about. So again, this module involves understanding deobfuscation, and steganography is one interesting application of that. Looking at the questions here, I think another one popped up. Adam is asking, will we learn to make an automatic malware analysis pipeline to perform config extraction of malware? So we certainly are going to target components of what could be an automated pipeline. With regards to config extraction, absolutely, we will talk about that. And you'll see here in an upcoming module, I'll give you a quick glimpse as to exactly what we touch on regarding that topic. Nicholas has taken a guess at this particular malware, so I'll leave that to your own investigation, or perhaps your time spent in this course with me. But you're not on the wrong track. I'll just say that. All right. So we in this first module talked about analyzing code deobfuscation. We then transitioned to program execution, and that's because that's essentially the next step, right? Once code is deobfuscated in memory, it's typically going to then be executed. That's the whole point of deobfuscating additional code in memory. So this next module targets the case where that next stage execution involves a full-fledged Windows executable. As you can see, this third module, which I'll touch on here in a few minutes, is another alternative case where shellcode is the next stage of execution. But let me briefly touch on what happens in this second module in section 1. So this slide lays out some of the key objectives of this module, and this involves understanding the Windows executable header, right, in more detail, understanding terminology and structures associated with the imports, with the exports, the steps necessary to actually execute a program. And as I read this off to you, you might be wondering, well, this sounds like kind of dry stuff, right? Not inherently malicious. And you're absolutely correct. None of this actually on this slide is inherently malicious, right? Resolving a program's imports, not malicious. Looking for the entry point, not malicious. In fact, these are all things that the Windows loader, the actual operating system, does every time you double click on a program and execute it. The interesting thing and how it relates to malware analysis is that if you are analyzing a loader, which is a type of malware that might perform that initial deobfuscation and be responsible for actually executing that next stage code, it has to do all this work. It has to do the heavy lifting. And so you need to be able to recognize code that is performing this work. Okay? In order to focus your attention on the bad, you got to still be able to identify the benign. And so although this activity, these steps, are not inherently malicious, you need to be able to understand and identify them in the code. And that's why we do have to go over this material. So just some excerpts from this particular module. We get into the actual header of the portable executable, right? This is the easiest part of that, looking at the MC header and looking at some other components of the NT headers. But then we get into some more detail around the data directories and how they point to, for example, the import directory table, the export directory table. We talk about what you can look for in the code to identify functions within a loader that are actually going to perform some of this heavy lifting. We talk in great detail about the terminology surrounding the import address table. So import address table is certainly one term we use to refer to the table of dependencies, but there's some other important terms that you need to understand to have a more comprehensive understanding of the important structures associated with a PE file. So this slide talks about some of the terminology associated with imports. This slide gets into some of the terminology associated with exports and what the Windows loader, like the benign Windows loader, the legitimate Windows loader, has to do in order to resolve an exported function. And the loader will have to do that as well if it's deobfuscating a DLL in memory, right? So this is all important terminology that we do have to have a baseline understanding of to go ahead and appropriately label and identify functions in our loader code that are performing this work. In this module, we also talk about the idea of mapping an executable into memory. Again, this is something that the Windows loader does every time you execute a program. But in the context of a malicious loader, we need to be able to understand the code and identify the code that is doing this work. A program on disk looks different than a program in memory that is about to be executed. We need to understand what those differences are. In particular, when it comes to dumping a process from memory, there's a difference between dumping an executable that is in its unmapped state versus an executable that is in its mapped state. So we need to talk about the differences between those two states and how to actually fix those up if necessary. So that's module 2, okay? An understanding of what has to happen for a loader to prepare to execute a Windows executable. In this third module of section 1, we then get into shellcode execution because that next stage execution might involve shellcode. So shellcode, as you might know, is a very streamlined executable content. There's no header that we can take advantage of. It's just the pure opcodes associated with the actual execution. If you've analyzed any Metasploit or Cobalt Strike, right, you most certainly have taken a look at shellcode before. Now, FOR710 does talk about shellcode as well to some degree. And in that class, we use emulators to understand very quickly and triage shellcode to understand what it might do. In this class, of course, we do a deeper dive. We want to look at the code itself. And again, the goal is to be able to label, right, to rename functions, to actually label individual instructions at a very deep level so that we understand comprehensively what the code is responsible for doing. So objectives for this particular module include understanding how to actually extract shellcode. That's probably the easy part. Well, certainly is the easy part. But then we get into understanding common techniques implemented in shellcode for obfuscation. API hashing is certainly one of them. Shellcode will also often touch the PEB, the process environment block. So we're going to discuss that structure. We're then going to use WinDebug preview, okay, which I think is an improvement upon WinDebug, in order to actually probe some of those structures in memory in order to better understand and describe what the shellcode in front of us is doing. And so we'll start using a workflow that involves not only a static code analysis tool like Ghidra, and not only a debugger like X32 or X64 debug, but also WinDebug, right? So we're going to put the information we get from all three of these capabilities together to more accurately and more comprehensively identify what code is doing. Now, this is just an example, again, of some of these slides. In this example, we are looking and we are identifying a function that performs API hashing, which again is one way that shellcode commonly obfuscates the functions that it's going to call. So a telltale sign of that is you see the same function called over and over again, and what's being passed to that function is just kind of this hexadecimal value, and that's actually the API hash, which is typically a combination of the DLL name and the function within the DLL that the shellcode actually requires. Now, in order to dig into API hashing, what you'll find is that it interacts typically with the PEB, the process environment block, as it iterates over DLLs loaded in memory and tries to actually identify the function it's trying to call. So we are, as I mentioned, going to talk about WinDebug. You'll have an opportunity to use WinDebug preview. I will talk about the various commands, how to set breakpoints, how to interrogate memory using WinDebug, with the ultimate goal of understanding the details of structures in memory. Now, I know this slide is crazy, and of course, it makes more context, more sense rather in the context of the course. But again, just trying to give you a glimpse at some of the technical detail we discussed. The goal of this slide is to take a closer look at the PEB and understand some of the various structures within the PEB, what they point to, and some of the specific fields within those structures, because these are all fields that are often touched by shellcode as it performs that API hashing to resolve important functions. Sean is asking, will there be any focus on .NET malware? Currently in the course, there really isn't any .NET malware, not because it can't be challenging, but because oftentimes it's just a matter of decompiling it and taking a look and taking your time with the actual source code. So at this point, I have not included .NET, but certainly if you have samples that you think are particularly challenging when it comes to .NET, I'd love to see them. That requires some more manual review. Please feel free to reach out to me. My Twitter handle, by the way, is @ASONI. So if you have any questions after this session, or you're watching the recorded version of this session, feel free to reach out to me, and I would love to chat with you further. So just some more information here on, oh, did I miss a question? Okay, I saw a question. Just some more information here on rounding out the discussion of API hashing. So based on what we learned from WinDebug and our knowledge of, for example, the process environment block, what you'll find is you can take that information back to, in this case, Ghidra, and then go ahead and start labeling and documenting what these instructions are responsible for and how they are definitively performing API hashing, right? So that's how we kind of use the workflow that involves a debugger, not only x64, x32 debug, but also WinDebug, and of course, Ghidra. Okay, so that's section 1. Is there any Apple Mac malware? I'm just reading a question here. Any Apple Mac malware? Do you think there'll ever be a type of focus on Mac malware? So there is no focus on Mac malware in this class. I think the honest answer there is that we haven't seen a demand for it. But if that demand increases, which I expect it will over time, perhaps we'll include something like that. But at this time, the class focuses on Windows executables. All right, so that's section 1, right? Code deobfuscation and execution. Section 2 focuses on encryption in malware. All right, now encryption is a pretty weighty topic, a pretty big topic. You could certainly investigate encryption for weeks, months, or years. Of course, the purpose of including it in this course is specifically to target how malware often uses encryption. In order to do that, however, we do have to start off with some essentials. And so this first module, that's titled Encryption Essentials, really just focuses on laying out some of the basic crypto terminology, asymmetric versus symmetric encryption, talking about some of the modes of operation you'll deal with when investigating symmetric encryption, talk about some of these specific algorithms, and then we'd also talk about the crypto API, which is commonly used to take advantage of encryption in malware. Again, the ultimate goal here is to be able to identify encryption in malware and assign some purpose to it, right? Why is there encryption here? Is it being used to simply encrypt strings, maybe a config file? Is it being used in the context of ransomware to encrypt files on disk? Is it being used to protect some of the keys used to encrypt files on disk? These are all different applications that we need to be able to identify. But before we can do that, we need to understand, at least at a high level, some of these algorithms. So here are just some examples, right? There are more. Some examples of the algorithms we tackle in this class. We're going to talk about AES, and how this algorithm works. Well, you'll have a better understanding of what an SP network is that involves substitution and permutation. We'll talk about initialization vectors, nonces, key scheduling algorithms, substitution boxes. Okay, these are all terms perhaps you've heard of before. You'll actually see how they're applied to each of these algorithms that we'll touch on in the course. This is an example of some slides we have on the various modes of operation, types of encryption that you'll often encounter when investigating symmetric algorithms. And so this is cipher blockchaining. And again, we'll get into what some of these terms actually mean, like how initialization vector is helpful for encryption, what are the pros and cons of different modes of operation, and of course, how to actually identify them in the code that you're looking at, so that when you write these deep dive reports, right, you can properly identify the algorithm and the mode of operation, if applicable, in the case of the malware that you are looking at. Other algorithms we look at, these are symmetric ones, include SALSA and ChaCha. Okay, these are sometimes used as part of ransomware to encrypt files on disk. And so we'll talk about how the algorithm actually works, and then, of course, how to actually identify it in the code. And so this slide gets into and starts introducing the details of these two algorithms, how they differ, and most importantly, how they actually process plain text data in order to produce that jumbled ciphertext. All right, so those are the encryption essentials. That's first module in section 2. Then we get into a very common application of encryption in malware, which is, of course, ransomware, right? So we're talking about encrypting files on disk, but also protecting the keys used to encrypt the file on disk, right? That's pretty crucial, because if the key used to encrypt the file on disk in ransomware was readily available to the victim, then they wouldn't need to pay anything, right? So attackers need to protect those keys, and that goes towards determining the purpose of the encryption you identify within a particular sample. So here are some of the objectives associated with this module, right? We dive a little deeper into specific symmetric and asymmetric algorithms in the context of ransomware. You're going to get a deeper understanding of those. I'm going to introduce a few automated ways to identify the algorithms, but also manual techniques, because sometimes these automated signature tools don't work properly or just aren't updated. New algorithms are coming out. So you need to be able to take the theoretical knowledge of how an algorithm works and apply that to a manual approach for finding code associated with these algorithms. And that's what we do in this particular module. Now, we also do talk about the crypto API, which is technically deprecated, but still used by malware. This is kind of the easy button from a malware author's perspective to take advantage of, because these are established, well-documented APIs. So certainly we'll show you in the context of a debugger and static code analysis how to determine if the crypto API is being used, and then support that with the good documentation that Microsoft provides, so we can determine exactly why or how this crypto is being applied. In this particular case, the malware is using the crypto API in order to import an RSA key that is embedded somewhere, I think, in the resource section in this case. And so that's something that we need to be able to determine. And then we'll, of course, follow on with how this RSA public key is actually being used. In this example here, we're looking at additional crypto API functions that are being used to actually generate, in this case, an AES key. So we'll talk about which arguments are important to determining that's the case. I'll support that with some knowledge from some Windows header files. And again, our goal here is to assign some sort of meaning and purpose to it. And in this case, the AES key is being used on a per file basis to actually encrypt the files, as ransomware commonly does. Now, crypto API, as I mentioned, is easy button, but not always the case. Sometimes the actual code associated with the algorithm is actually embedded in the program. So we need to be able to recognize more manually where these algorithms reside. In this case, on this slide, we're talking about ARX algorithms, which stand for algorithms that involve a lot of add, rotate, XOR operations. SALSA and ChaCha both fall into that bucket. And I'm showing you here how to identify SALSA and ChaCha just in some code. And then we can proceed to actually debug functions where we identify this in order to determine exactly the purpose behind this particular encryption. Okay, so that module, right, dives deeper into ransomware and its application and implementation of encryption. Next, we talk about data encryption in malware, right? Because this is yet another common use case for encryption in malware, not necessarily to encrypt files on disk, but to encrypt strings or to encrypt, for example, a configuration file, right, or config data associated with that particular sample, right? Maybe something that dictates various C2 servers or certain processes that it's injecting into, maybe some key information. Those are all examples of what might be in a config file. So purposes of this module include, again, understanding some of the popular encryption algorithms that are used for data encryption. And the neat thing about data encryption and where it can benefit us, or at least an advantage of looking at data encryption in malware, is that at some point, the expectation is that data is decrypted, right? So if it's a config file, at some point, that config file is going to be decrypted in memory, which means with the appropriate knowledge, hopefully we can identify not only the algorithm, but the actual key. And then we can go ahead and decrypt that offline outside of the malware. That's the ultimate goal in many cases when understanding data encryption in malware. So one algorithm that's popularly used to do this is RC4. So we do a bit of a deep dive into RC4. RC4 can be broken down on the left-hand side into the key scheduling algorithm, that's the KSA, and the pseudo-random generation algorithm, that's on the bottom left here. In the class, we get into details about what those mean, and most importantly, how those correlate on the right-hand side with actual code you'll be analyzing within Ghidra. And in this case, we're using the decompile window to kind of expedite our analysis. All right, so identifying an algorithm like RC4 in malware is the first step. Okay, but then we want to actually extract the key length, extract some sample encrypted data, and then try and actually decrypt this. All right, and then I'll talk shortly here about how we can even automate that process. All right, let's see here. I think I saw some bunch of questions pop up. Adam's asking, will we be looking at real modern malware in the course? So the simple answer to that is yes. And by that, I mean, all the malware in this course is real. I didn't create any of it. SANS didn't create any of it. It was all, found publicly. It's all in VirusTotal and in many other virus databases. And so it's all real stuff. And it's all certainly relatively recent. None of it's like a decade old, anything like that. The purpose of this class is to impart practical knowledge so that a week, days after, maybe even during the class, which happened during some of the betas, maybe even during the class, right? You'll get a case, start working it, and be able to use this information. So the hope is that this is very practical information that you can apply to malware that you'll see the very next day. Nicholas is asking, will there be more classes in the autumn, and will there be live in Europe? So the answer there will be yes. Right now, I don't have a timeline for you. This is, of course, a brand new class. We got our first public run in a week and a half. New classes will be scheduled very soon. They'll include live online. I hope they'll include live classes as well. As I mentioned, on demand is on its way too. So all the typical vehicles for SANS courses will be available in the not so distant future. That's just kind of, that engine is still kind of getting warmed up. I got some more questions here. Will there be a balance of using IDA and Ghidra, or is one used more than the other in this course? I was waiting for this question, right? Very controversial topic, of course, very heated debate over IDA versus Ghidra, and the decision that Laney and I made in 610 to go with Ghidra, and 710 continues that trend by focusing only on Ghidra. So there is no IDA in either 610 or 710. And happy to chat with you about that further offline if you like. But we did make the decision to go all in with Ghidra. It's got that decompiler, allows us to script out of the box. And from a learning educational perspective, it just seemed like the right choice to me. So that's why this class does focus on Ghidra. If you've never used Ghidra before, if you go to the course registration for this website, there is another YouTube video I put up a while ago that introduces the workflow of analyzing malware at a code level using Ghidra. So I advise that you watch that before you actually attend the course. There might be, it might be a little painful for the first few hours as you get acclimated to Ghidra, but at the end of the day, these are just tools, and they do very similar things, right? We can debate the nuances, which one does something better than the other, but they're just tools. You can implement the same workflow, a very similar workflow with both. That's some more questions, I think. Michael's asking, do we have to follow 610 before this training? Thanks. So there is no formal prerequisites for SANS courses, right? No one's checking to see that you took 610. It's advisable that you've taken 610 or have similar knowledge and experience. That's the way I would put it succinctly. I got another question from SpiffySec here with the CTF. Is there a coin, and what does it look like? All right, yes, there is a coin. It actually got created not too long ago. Currently in the mail to me right now is the first coin. I haven't seen it yet, but I do have a graphic to show you what the demo kind of looks like. So I will show that here in just a bit when we get to the CTF. All right, I think I hit all the questions. My apologies if I missed any. If I did, just help me out, maybe repeat it again, but I think I hit all the current questions. So section 3, right? This is where we talk about the entire section 3 is dedicated to automating malware analysis. All right. The first one introduces Python for malware analysis. Now, keep in mind, this isn't a Python course. In fact, SANS has an entire class dedicated to automation with Python that you're welcome to check out. Really, really nice course. And so I think I'm going to throw out there 573, but if I'm wrong, one of the folks at SANS can help me out with that. That's an awesome course. I've taken it before. But this particular module introduces Python for malware analysis. And going to a question that I saw earlier, my apologies, I can't remember who asked it. The ultimate goal of this section is to create a standalone configuration extractor, right? That's a very practical use of Python for malware analysis. And so we kind of build that up a little bit. I'm not assuming you've used Python before, although that certainly is a nice thing to have in your back pocket. So I do take some time to introduce the basics of Python, but then we get right into creating a config extractor. We take advantage of the knowledge from prior modules. So as you can see here on the screen, in this sample walkthrough that I discuss, we talk about RC4, we identify where the key is embedded in a program, where the encrypted content is, and some other supporting information. And then we learn how to use the PE file module in Python to actually pull that information out automatically and essentially create a standalone config extractor. So this is a really good application of automation and the information that's discussed earlier on in the course. Next, we get into malware analysis with DBI frameworks. Now, DBI stands for Dynamic Binary Instrumentation Frameworks. It's really just a fancy way of saying that these are essentially tools and capabilities that allow you to intercept calls to functions. They allow you to take a look at the internals of a function, manipulate, even if you desire, arguments being passed to it or return values passed from it. And the reason we talk about DBI frameworks is because those things I just described, intercepting API calls, looking at return values and arguments, is exactly what we typically do in a debugger. And so DBI frameworks allow us to automate the debugging process. So you still have to do that manual work up front. But once you've looked at a few samples that essentially have a similar workflow when it comes to analyzing them in a debugger, you can use a DBI framework to actually create a program to do that for you automatically. And that's what this module focuses on. Now, there are a variety of DBI frameworks out there. The one I've chosen for this course to focus on is called Frida, okay? And so we talk about how to use Frida and its Python bindings in order to create some pretty nice scripts that automate common debugging workflows. Here's a quick example of one workflow we discussed automating. If you've done some debugging before, you've certainly paid attention to virtual APIs like virtual alloc and virtual protect. Virtual protect is one of those APIs that's responsible for modifying the permissions of a memory region. Now, generally during malware analysis, if we see virtual protect called and it's updating a memory region's permissions to be executable, well, perhaps there's some executable content there. In this case, if we take a look at the region that's referenced right here, and we look at it in the dump window where we have visibility into a memory region, you'll see that there's an MZ header. Now you'll see there's some stuff after an MZ header, which might be familiar to you if you've done cases that involve this particular type of sample. But the bottom line here is this is a common workflow that allows us to identify some next stage executable content. We'll then talk about how to actually code up a quick Python script that also has some JavaScript. Yes, some JavaScript, just a little bit. And the program we create will actually, as you can see here on the top left, a demonstration of the program. It'll actually find automatically those memory regions and go ahead and dump that executable content down to disk. And in this case, we see that there is a 64-bit DLL there. Okay, so DBI frameworks are an awesome application of automation within malware analysis, and that's one that we're going to talk about. Finally, we talk about automating analysis within Ghidra. Okay, and specifically, we're continuing to focus on Python. So all these modules focus on Python for obvious reasons, right? Great language for automation, fairly easy to learn. And so although within Ghidra, you can use Java too, which we won't get into that, or you could also use Python given its implementation of Jython. We are going to go ahead and use Python. And the end result, again, is to try and create a Python script within Ghidra to automate some of our work. Now, I'm not going to get into the details of the script you see on the left-hand side, but one application we discussed is to identify functions of interest. So you might recall I referenced ARX operations earlier on, maybe about 15 minutes ago when talking about salsa and cha-cha. ARX, again, is add, rotate, XOR. That's a type of encryption algorithm you'll encounter. And so basically, we code up a script together that allows you to identify functions like that, which can allow you to hone in on functions that perform encryption or decryption, right? So the identification of functions of interest is one application, and that's what we're looking at here. Section 4 is essentially the smallest section. This ends up being just basically the last half of the day of day 5 of the live course. And this goes towards correlating malware and building rules. So we're taking advantage of what we've discussed before, the code analysis, encryption algorithms, and we're now taking advantage of that information to understand the similarities and differences between malware. When you can identify similarities and differences, you can start to build malware families, you can start to build rules like yara rules for these samples, and in general, you can just expedite your analysis, because if functionality is very similar today for a sample that you identify compared to a sample from last week, well, you might have saved a lot of analysis work. I introduced certain tools like bindiff for code level analysis, Ghidra's also got a built-in program diff feature that allows you to do pretty in-depth code level analysis. I introduced that as well. I also introduced some custom tools I have to kind of help compare some basics of binaries, like their imports, strings, other aspects of a program that you'll generally want to compare when doing either a one-to-one comparison or one-to-many comparison. Okay, so that's what this first module talks about. In the final section, as I just hinted at, we then talk about yara rules. Yara rules are obviously helpful for taking knowledge you have about a particular sample or group of samples and then generating these rules to hopefully identify similar samples in the future or similar capabilities in the future. So we talk about yara best practices, and you have an opportunity to write a rule here in class as well. And then finally, we get into building COPPA rules. Okay, now COPPA, you may have heard of, is a pretty awesome capability that was developed by the folks at Mandiant. So definitely encourage you to check it out by going to the URL at the bottom of the screen here. Now, it can be used for triage out of the box without doing any sort of rule development. But what we talk about here in class is how to actually create your own COPPA rules in YAML in order to take advantage of what you've learned about a sample and its capabilities to identify similar samples very rapidly. And so essentially, going back to that same example I showed you in Ghidra, where we created code to identify ARX algorithms. In this particular case, you'll see that the YAML rule I'm using here is purpose-built to identify ARX operations in an arbitrary file. And by running COPPA in this manner against a file here, system32.exe, it's able to identify with the rule that we create in class an algorithm automatically that includes ARX operations. And in this case, it's an application of Saucely or Chacha in this ransomware. Okay, so that's yet another way that you can automate some of your analysis. Now let me just check here on questions. Username is asking, does FOR710 cover opaque predicates and control flow flattening obfuscation techniques? So this is one that I really wanted to include, and I may include in the future. Just couldn't squeeze it in the content I have here. Okay, so it's like basically the next thing, the next module I would create if I had room for it. Thinking that over, but right now it is not currently included in the class. Imran is asking, how can we prevent malware using anti-emulation techniques? Anti-emulation techniques. So Imran, if you have a particular technique you're thinking of, let me know. We don't get into anti-emulation techniques in particular here. If you're talking about like malware that executes within like a VM or something, that's not something we touch on here yet, in part because while certainly there are cases of it out there, the time that we're required to really get into that and kind of custom instruction sets that are sometimes present within these micro VMs that are executed, the benefits of going over that just weren't there, because I'd have to push something out of the course that I personally think is more critical. But again, if you have some examples that you're thinking about, some samples you've dealt with, I would love to see them, because the content in here obviously is always a work in progress. Let's see here. LinkedIn user, does the course cover fileless malware analysis? So 610 actually covers fileless malware analysis, so we don't cover it in this course, but 610 does, I think, cover that pretty adequately. All right, I think I got the most recent questions here. Cool. All right, so finally, let me just say a few words here about the malware analysis tournament. As I mentioned, it's an extended malware analysis tournament, which means you have 2 weeks after the last day of lecture to actually complete the course. I think there are a few benefits to this approach. One, the course was designed from the beginning to be 5 days and 5 days only. So if I did 4 days of content, then I have to do 1 day of a CTF. And I wanted to maximize the time for lectures and labs. And the CTF generally is something students do on their own anyway. So I decided to maximize the information I can impart to you and the runtime with labs in the 5 days of content, and then have you do the CTF once those 5 days are complete. And frankly, I think this represents more realistically the deep dive environment, because again, when you're doing deep dive malware analysis reports and analysis, you generally don't just have a few hours, you have days or even weeks. And so I'm providing you with days and weeks to actually chug through this, instead of this kind of arbitrary time pressure to get all these questions done in just 4 to 6 hours, okay? So you're going to be using the Ranges.io platform that some SANS courses are starting to use, a really nice platform for CTFs, and that's what we go ahead with. And you'll have a variety of multiple choice and short answer challenges to ask, or to answer rather, along the way. And of course, the most important part of the CTF, the coin. Okay, so this is what the coin looks like. Again, we just designed it a couple months ago. The first one is on its way to me right now. But my goal with this coin when we were designing it was to kind of obviously make it look as cool as possible. But most importantly, to make sure it's dripping with the key skills I hope you'll take away from this course, which is better understanding deobfuscation, automation, and correlation. And that's really all I had to share with you here today. If you have questions, I'm still around, right? We've got technically 15 more minutes here. If you have any other questions, but if you are going to be heading out soon, thank you so much for joining me. Remember, go to sans.org/FOR710 if you're interested in learning more about this course. I really hope you'll join me for an upcoming class, and hope you enjoy the rest of your day. I'm just keeping an eye here to see if we have any other questions as we round out this session. Nicholas asked, how do we win the coin? Well, the way you win the coin is to get the, yeah, I mean, essentially each question has points associated with it. So get the highest points, you win the coin. And those are really all the requirements, right? Just to get the highest score possible. Some people have had exposure to Kapa. That's awesome. Yeah, definitely great triage capability. All right, so I'm not seeing any other questions pop up. Again, if questions do come up after this live session, or if you're seeing the recorded version, please reach out to me on Twitter at ASONI. Again, my name is Anuj Soni. Thank you for joining me here today, and hope to see you in an upcoming class.